Hello, Royals. Let's talk about lesson 7.4 on future values of annuities. What I want to do in this lesson is, again, stress the importance of avoiding the memorization of more complicated formulas, and then we will take a look at a different type of annuity. So let's revisit a retirement problem. We want to have $1 million, but unlike our example, we are closer to retirement. Let's say we want $1 million after 12 years at 6.2% per annum compounded biweekly. We're investing at the end of every biweek, and we should also be able to calculate the interest. So let's start with the timeline. There we go. This is going to be, we have a little calculation to do, I suppose. The number of compounding periods and the number of payments is going to be that we're investing for 12 years and we're investing bi-weekly. So 12 years of investing and 52 weeks in a year, so 26 bi-weeks in a year. 12 years of investing, 26 investments per year gives us 312 investing periods. The fact that we are making deposits biweekly and interest is compounded biweekly makes this a simple annuity. And we only look at simple annuities in this course. I'm going to take another run at the focus here. Try that. The fact that we are making these deposits at the end of every bi-week is what makes this an ordinary annuity. And that doesn't make a ton of sense when we are saving. It'll make more sense when we're talking about present values in 7.5. It does simplify the calculations for us, and unless otherwise stated, every annuity in our course is a simple ordinary annuity, but we will want to look at a non-ordinary annuity in a sec. So here is the end of the first bi-week, the end of the second bi-week. Time passes. Here is the end of the 312th bi-week. This will be the 311th bi-week. And the way that we deal with an annuity is just splitting it up into a bunch of lump sums. We're going to make a payment at the end of the first bi-week, a payment at the end of the second bi-week, and then for some reason we're making a payment at the end of the investment period that doesn't have a chance to grow. We're going to track these for future values because we want to have $1 million in the future. This is the weird thing about the ordinary annuity. Your last payment doesn't have a chance to grow. This payment right here is going to have a chance to grow at, I'm going to do this in the general case actually, 1 plus I to the exponent 1. And then we have a bunch of payments, and let's just track this last payment right here. And we could do this in the specific case or in the general case. In the specific case, I'm going to realize that the 312th payment had 0 chances to grow. That means that the first payment is going to have only 311 chances to grow. This should look an awful lot like our geometric sequence where we have a first term times a common ratio to the exponent 1 on our second term, and by the time we get to our nth term, t sub n, we only have n minus 1 multiples of r. The other way to get this number correct is just pretend that there were 1, 2, 3, 4 payments instead, and track this payment. Watch how it only grows 1, 2, 3 times, not 4 times, and minus 1 times. Okay, we add all of these up, and this sum right here should be our future value. So if we're interested in using a formula for future value, all we need to do is have our formula for the sum of a geometric series, which we proved, but did advertise as saying if there's one formula you're going to memorize out of Unit 6, it might be this one right here. Okay. My sum of the series is my future value, or my future value is the sum of the series. I'm going to decide, notice my decision here, I'm letting, and I made this decision without asking you about it, as if you could reply. I'm making the last payment my first term, and the first payment my last term. And the reason why I'm doing that is so that my R value is a power with an exponent that is positive. It makes it just a little bit easier. If I had a series, and this was my first term and that was my last term, I would just reverse the series. So that R is my first term. Capital R is my first term. And then my common ratio is just going to be 1 plus I to the exponent 1. The n in the number of terms in a geometric series is the same as n, the number of investment periods in this simple ordinary annuity. And then the other little change that we do, our denominator of our common ratio minus 1, if my common ratio is 1 plus my compounded interest rate, I just do the minus 1 automatically. 1 plus I minus 1 will become I. That's why I think you don't have to memorize this future value formula. Okay, you shouldn't bother memorizing it if you have this down, and you should have this down because you're going to need to use that for Unit 6 material. Then you know how to deal with this question anyways. Okay. Let's substitute in the specifics here. We know our future value, or we want our future value to be $1 million. We don't know how much we are investing or how much we need to deposit at the end of every single bye week. Most people get paid every bye week, so this will be like the end of our pay period here. 1 plus, let's see, we are receiving, or we're advertised that we're getting 6.2% per annum, but actually we're getting 0.62 per 26 per bye week. There's 312 terms. We subtract 1 and we divide that by 0.062 divided by 26. Now note my extra bracket, note my extra bracket down there. Not really required in the formula, but when I do some calculator work here, I'm going to need it. For calculator use, strongly recommended that you do not round this number off. We try to teach students to touch their calculator once. We shouldn't be typing in 0.062 divided by 26, and then we round that number off to like 0.002. We add 1, we raise that to an exponent 312, and any rounding we do here is compounded. Same verb, compounded by that exponent. So try to type this in one go. You could rearrange here. You could write it as 1 million times this divided by that. But there is an option here. If you round this entire number off to a couple of decimal places, it doesn't cause a huge issue when you divide 1 million by that rounded number. I'm going to try to advertise using an answer button or a memory key on your calculator. Most calculators have what's called an answer button. So here's my plan. I'm going to type all of this in. I'm going to try it in one go with a bunch of brackets. And then I'm going to hit enter or equals. And then I'll do 1 million divided by that answer. And that'll be what R will be. Okay. So in the numerator here, I'm going to be typing in a bracket 1 plus 0.062 divided by 26. Close that first bracket to the exponent 312. Don't need a bracket there. Minus 1. Close that bracket. Divided by bracket 0.062 divided by 26. If you use a fraction button, you don't need as many brackets as I have. Right. That should be my growth factor. I divide 1 million by that answer. 1 million, 3, 4, 5, 6 divided by that. And here's my answer key all the way down here by that answer. And it spits out this number. Now I'm happy that this number is positive. And I don't know. I mean, it seems like an awful lot to have to deposit from a biweekly paycheck, but this person is hoping to have $1 million 12 years from now. Hopefully they have some other savings. The easiest way to check the reasonableness of this answer is with your shoebox analogy. Okay, and so I'm pretty sure this is the right answer because I've done this question a couple of times, but let's double check it by answering how much interest is earned here. Right? So a quick way to check the reasonableness of this answer. This person made N payments of R. They made it into a compound interest fund though. So they made 312 payments of about, I am rounding off here to the nearest cent, $2,162.97. Right. The reason why I call this the shoebox or the mattress number sounds a little weird. Is imagine this person, instead of depositing into this fund earning 6.2%, imagine they just put this money into a shoebox or under their mattress. then they would have saved up a significant chunk. They would have saved up $674,846.64. And this lets me know that I think there was lots of opportunities to make mistakes here. This lets me know that I think that I didn't make any mistakes, because this number is a little bit, or significantly in this case, it's less than $1 million. And the difference, the reason why, if this person just put the money under their mattress, they wouldn't end up with $1 million. Or rather, the reason why if they invest in this fund, they would end up with $1 million. The difference there is interest. Okay, so I like referring to this as a shoebox. You can use that term if you like. But then here comes another formula. I mean, that seems like a formula, but is it really? To think, okay, I made this many payments at that much, that operation should make sense. This operation should make sense as well. That my interest here is going to be my future value minus the contributions that I made. Or let's try it specifically with the numbers here. If this person invested at 6.2%, compounded biweekly, then they end up with $1 million, but they only deposited $674,846.64. So why is that different? Interest is why. I'm subtracting 1 million, and then I'll just reverse the sign there. That gives me $325,153.36. Now, this isn't nearly as impressive as the example in the lesson where someone was investing for 30 years, where it was something like 70% of their investment was actually interest. Here, it's more like a 60-30 split kind of thing. 12 years is still a decent amount of time, but trying to save up $1 million in 12 years is going to cause like significant, this would be difficult for most people to afford, let's say, to deposit $2,000 out of every single paycheck at the end of every bye week. Okay, we should write some conclusions on here. They must contribute this much every bye week, and this much is earned in interest. The word earned, think of that as like through a financial lens. I'm not sure that this person has deserved this money, right? They are loaning the bank their money, so they're being paid for the privilege of not having that money anymore. Okay. All right. The other thing that I want to look at is the annuity due. In a simple annuity due. Sorry about the shake. Can we fix that at all? Maybe. It's a simple annuity because our compounding periods are going to line up with our deposits. But in an annuity due, your payments or deposits are made at the start of periods instead of the end. Okay. This should make more sense through a saving lens. It doesn't make as much sense through a borrowing lens. Okay, let's find the future value of n regular payments of our dollars at I% per annum compounded. Actually, well, I% per compounding period. That'll make it a simple annuity. At the end. Sorry, beginning, at the start of each period. This is going to create another formula for us, and it can stress students out. I remember it concerning me when I was in a finance class at university. It felt like there was dozens of formulas that I had to memorize, and I wish I had developed more of an understanding so that I realized I didn't actually even need to memorize all these formulas. It's all just geometric sequences. Let's draw this out. Timeline. Here is the end of period N. Here is the end of period 1, period 2, squiggle, squiggle, period N minus 1, right there. Okay. We're making regular payments, except what we're doing, let's imagine we're saving up here. So why don't I make a payment right now or a deposit right now and let it grow? And then I'll make a deposit there and a deposit there, and I'll make a deposit there. But I'm still just making end payments. Why would I make a deposit at the very end? Because it doesn't have a chance to grow. So really what we're doing here is we're not adding one more payment. We're just shifting these payments back one. It can look a little bit weird because it looks like, oh, look, there's still a payment at the end of period 1. This isn't the payment at the end of period 1. This is the beginning of period 2. This is payment number 1. This is payment number 2. It's just payment number 2 is happening at the beginning of period 2. Payment number 1 is happening at the beginning of period 1. This is payment N right here. We'll track their future values. Let's do this one first because it has the shortest time to grow. But look, it has a chance to grow, unlike in our annuity due. And then let's put in another one right here, N minus 2. That payment right there, our N minus first payment, is going to have one chance to grow. Or sorry, 2 chances to grow. 1, 2, growing over 2 periods. Bunch of payments. Here is the first payment that we're making, which we're going to treat as our last term again, so that our exponents, our common ratio, is a power with a positive exponent. It simplifies our calculation significantly. This one right here, growing at 1 plus I per compounding period, and it grows for 1, 2, let's pretend there's 1, 2, 3, 4, 5. It's growing for 1, 2, 3, 4, 5 periods. It grows for as many periods as we have. So things should look very, very similar. We have a different first term. Our common ratio is still going to be 1 plus I, and we still have N terms. The N compounding periods, the N payments that we're making, is still going to be the same as the number of terms that we have. So there's so much similar here. The only thing that's different is the first term that we're dealing with. We can still use the sum of a geometric sequence formula. Series formula. We'll be using this in 7.5 as well. So focus on that. There's not like 6 different formulas to memorize. There's one. Our future value here is going to be, all right, let's see, my first term is going to have a chance to grow. So it's going to be R times 1 plus I to the exponent 1. My common ratio is the same as before, 1 plus I. And there's going to be N of them. I still subtract 1 there. And then I'll do the same subtraction in the denominator here. This 1 plus I minus 1, I'm just going to simplify down to I. And that's my future value of an annuity due. Instead of flipping the page back and forth, what I'm going to do is I'm going to write down the formula that we built for a simple ordinary annuity. It was R times 1 plus I to the exponent N minus 1 all over I. I would imagine I don't have to imagine, it's very difficult to try to memorize all of these. But this really should make sense because in an annuity due, I'm not making one more payment. I'm shifting my payments so that every single payment has one more chance to grow. So my future value, all of my payments together have one more chance to grow. And that's where you might notice that the future value of an annuity due is actually the future value of an ordinary annuity with just one more chance to grow. You're just putting in a factor of 1 plus I on every single term there. Okay. try to minimize the amount of memorization. You need this formula memorized anyways for Unit 6. We developed it, but its development was harder than the Gaussian approach to arithmetic sequences. So get this one down, and then future value of annuity due and future value of ordinary annuities, it'll fall into place. And the exact same thing is going to happen in our next lesson. That if you understand it and you build through an understanding instead of memorizing, you're going to have a deeper understanding, and you'll do much better on tests. You won't be cramming the night before, and you'll do so much better in future courses and on exams where maybe you feel like there's too much to be memorized. It's also very important that you practice this material, practice doing the development yourself, and try out as many questions as possible. Give it a shot.